Well, thank you for the introduction. Thank you also for the invitation to come here and participate in this Moonshot event. I also want to congratulate the Japanese government with this Moonshot program. I'm very impressed, especially also with the long time scale, the long time horizon, thinking about ambitions towards 2050. So anyways, it's been great to be here, and I'm happy to tell you about some of our own work. At this event, we're obviously hearing about many different qubit implementations, and the progress all around is really impressive. What I want to take as a motivation for the semiconductor approach that I'll be discussing is, if you look at the development of conventional transistor technology, it's quite remarkable, right? A few years after the transistor was invented, you could already buy commodity products like a transistor radio. It had already value. That's quite remarkable. But at the same time, the way that this transistor radio was assembled, it's not a scalable approach. It's hand soldering components together, transistors, capacitors, resistors, and so on. So that only will take you so far. That, of course, dramatically changed when the integrated circuit was invented. And actually, that's now, of course, driving the information revolution of today with billions of transistors integrated on a integrated circuit. They all work together, and it's just really impressive. So looking at our own field, we have, of course, this promise, right, of quantum computers solving important problems, in physics, simulating molecules, simulating materials, and so on, which can in turn really impact, societal problems, or can help address these societal problems in energy, batteries, energy harvesting, who knows, perhaps as room temperature superconductor, or designing efficiently new medication, better fertilizers, what have you. Also, of course, related to the Shor's algorithm, that can be impacting security and code breaking. But different from these early transistor examples, the current technology that we compete with is very different, and it's basically, putting the bar very high. And with all of the knowledge of today, if you want to solve a relevant problem that cannot be solved with any other technology, it requires, with the best, again, relying on the best knowledge and concepts of today, it requires many millions of quantum bits that all have to operate together, and where errors are corrected or removed faster than they appear. So that's quite a challenge. So then, for me, a question is, how do we go from really, kind of trend-setting experiments, such as these so-called quantum supremacy experiments, to a device that can solve a real-world problem, a relevant problem, can solve it faster than any other computer, or can even solve problems that are beyond the reach of any other existing computer. I would argue, as Michel has done, but then with a slightly different twist, that if you start from semiconductor technology, that is a powerful starting point. As we've seen how much integrated circuits have brought to the world, if you could build or leverage the same technology to build quantum bits, that's a good starting point. And of course, a transistor, basically controls the current between two contacts by modulating the voltage on the gate that sits on top of a channel. In the quantum dots that I will show schematically, this same transistor is used, but now the two contacts are separated a bit more, allowing space of multiple separated gates, multiple split gates. And these split gates allow you to modulate the potential landscape in the channel. And so you can form local potential minima, where quantum dots can be formed. In each of these potential minima, in each of these quantum dots, it is routine now to isolate just one single electron. And that's a completely stable situation. If you've cooled down your device and you trap one electron in each of these quantum dots, you come back the next day, the next week, the next month, the next year, it will still be there. It's very, very stable. I do want to point out, and this is important, that the quantum dots are actually formed in a buried layer. It's basically a quantum well consisting of silicon separated from by a silicon germanium barrier from the dielectrics, from the surface, from the metal on top. And that is actually important. Michel spoke about the importance of charge noise in these structures. It's important because most of the origin of charge noise is at these interfaces, at the dielectrics. And so instead of having the quantum dots right against the top surface in the dielectrics, we bury them in a quantum well. These quantum wells, in all the work that I will show today, are grown in the group of Giordano Scapucci at QuTech. Most of them, of the work that I'll show today, uses silicon quantum wells, but there is also some work at the end where the quantum wells are actually formed from germanium. So with one electron in each of the dots, the spin of each electron for us is a quantum bit. There are other encodings that people study where 2 or 3 spins collectively act as a single qubit. So far in our group, our focus has been 1 spin, 1 qubit. It's kind of the canonical qubit, right? That spin electron, sorry, a spin 1/2 of an electron, the canonical classical 2-level quantum system. So based on this concept, we have been working on the building blocks of a vision that is laid out here of what a large-scale quantum computer might look like. And it consists of local registers. I don't know yet what their size will be. You know, is it going to be 2 by 10 or rather 20 by 20? But some size, not 100,000 by 100,000. And then many replicas of those local registers, which all exist on the same chip. So the entire picture here, plus the space around it, is one chip. And these local registers are then to be connected with quantum links, so that they can act as one large entangled quantum system, one large quantum computer. And where in between there is also some space to embed on board some classical circuitry. Classical circuitry built with the same technology as is used to build the qubits. It's kind of very natural. And this can actually help overcome the wiring bottleneck, which is one of the most important practical bottlenecks that you otherwise face. Every qubit needs, well, simply speaking, let's say that every qubit needs a single wire to reach it. It's not going to happen that you bring in 1 million wires from the outside to this semiconductor chip. So instead, the vision is bring in a manageable number of wires and then distribute signals across the chip using some classical demultiplexing electronics. What I will focus on in the talk is progress on the local registers, both in the qubit number and in the quality of the control. I will speak about 2 methods that we're trying to work on or trying to implement quantum links. I won't have time to go much into the discussion on integrated electronics. We have done work on this, some of it together with Ryoichi Ishihara from QuTech, and some of it with our colleagues at Intel and our electrical engineering colleagues in Delft. So starting with the quantum registers, these systems are actually quite high quality. Well, they have evolved to become quite coherent, well-controlled systems. Different from gallium arsenide, which was the materials platform of choice in the early years, and where we were very much limited by decoherence from nuclear spins. In these isotopically enriched silicon structures, and actually for us, Michel, our silicon comes from the Netherlands. It centrifuges in a company called Urenco, and it's just available and at a reasonable cost. So in these isotopically enriched silicon devices, coherence can be long-lived. T2s of up to 100 microseconds. With dynamical decoupling, these timescales can be extended to tens of milliseconds. Single qubit fidelities, as in this data from the Terucha group, this is from the Zurich group. Single qubit fidelities are now routinely over 3 nines, in some cases reaching 4 nines. The single qubit control in our first experiment back in 2006 was done using magnetic resonance, just an oscillating magnetic field on resonance with the spin frequency. And more lately, pioneered by the Terucha group here, more and more the method of choice has been to use not oscillating magnetic fields to drive the spin, but rather oscillating electric fields to drive the spin. That has some practical advantages. Now, electric fields do not naturally talk to spin, so you need some spin orbit coupling, which can be either intrinsic to the substrate or, like here, is artificially introduced by having a piece of cobalt or some other micromagnetic material sitting next to the quantum dots. That micromagnet generates a static gradient in the magnetic field. And if you now imagine using an oscillating electric field that you wiggle your electron back and forth in this magnetic field gradient, just like I think Ferdinand spoke about this for the ions. Or was it Jonathan? One or the other. So also here, you know, if you move your electron in this field gradient, it experiences an oscillating effective magnetic field, and if you do that at the right frequency, you can drive spin resonance. So that's been working well and well under control. But what has been an outstanding challenge for quite some years in our community is to demonstrate that also the 2-qubit gate can be implemented with high fidelity. And so we set out to do that a couple of years ago, aiming to go at least beyond this 99%, which is, of course, not a holy number, but it's sort of a representative target of you know, hopefully achieving full tolerance. The 2-qubit interaction arises from the overlap of electron wave functions. So we basically lower that potential barrier separating the two quantum dots so that the two electron wave functions can overlap a little bit with each other. And when that happens, you naturally get a Heisenberg exchange interaction acting on the spins. Now, because of the magnetic field gradient from the micromagnet, the spin splitting of the left and the right dots in this device, these spin splittings are actually separated from each other. There is a difference in their precession frequency. And that actually suppresses the effect of the flip-flop terms, the XX and the YY. So what we're left with is a Ising interaction, ZZ. And we will try to gently turn on the Ising interaction and then turn it back off, so that adiabatically we can get a controlled phase evolution. We really took some care in ensuring, you know, a high degree of adiabaticity, keeping in mind that you want to, you know, gently turn on and off that interaction. It's kind of going through this smooth profile, and keeping and taking into account that if you change your gate voltage, it changes the interaction strength, not in a linear way, but in a non-linear way. So we kept that in mind. We also operated at a so-called sweet spot, where to first order we're insensitive to charge noise. And finally, we used gate set tomography to characterize the remaining errors in our operation and use that to, you know, as part of a feedback loop to kind of make some final adjustments to the calibration parameters. And so with these efforts, we could really routinely push the 2-qubit gate fidelity in this 2-qubit device, I should say, beyond 99.5%, actually up to 99.65%. This work was published about a year and a half ago now, and what was really gratifying to see is that this was not, you know, a result achieved on a specific day when the weather was nice, you know, or on a specific device which was lucky. No, it has been reproduced across several labs. So in addition to our own work, there was the parallel work from the Tarucha group, actually also on heterostructures grown in Delft by Giordano. And there was also the work from the Morello group at UNSW using the donors that Michel spoke about. So, and then a bit later, the PETA group also achieved 2-qubit gate fidelities above 99%. So this is something that can be done and can be reproduced, and that's, I think, a good place to be in. So this was just, you know, operating on 2 qubits. There has been attempts over the years to go beyond 2 qubits. You know, like a couple of years ago already, we had entangled 2 qubits. Fidelities were around 90% back then. Menno Veldhorst at Delft showed full control of 4 spin qubits. This was on these germanium quantum wells with Hall spins instead of electron spins. And the Tarucha group 2 years ago demonstrated entanglement of 3 spins, 3 electron spins. Here I'm going to show you results on a 6-dot linear array. You see how these green and blue gates, finger gates, sit on top of a channel. You know, that's kind of what I tried to illustrate before. This is used to shape the potential landscape. And at the locations of these yellow circles, quantum dots are formed, occupied, well, you could say by 1 electron each. In fact, for technical reasons, 2 of the quantum dots we we placed 3 electrons instead of 1 electron. It made the readout easier, but also 3 electrons. You imagine a closed shell, and then one electron on top of that can act as a spin 1/2. You also see 2 larger quantum dots on the side. These are charge sensors, and they will be used to help read out the spin states. The way we read out the spin states, similar to what Michel described, is we make electrons move or not move, depending on their spin state. And so these charge sensors pick up the motion of these electrons, and then we can then infer this was a spin up, this was a spin down, and so on. In fact, what we did, well, let's see, maybe for the sake of time, I'm going to skip some of these details here. Let me just mention that in this experiment, one innovation is that we initialized by measurement and real-time feedback, and then adding real-time feedback. So you start with random spins, you measure them, project them, and some of them end up in a desired state, others end up in the opposite state, and then you flip them and continue. So this is how we initialized this device, initialization by measurement. Here you see Rabi oscillations taking for each of the 6 spins one at a time. I mean, the 6 spins are there all the time, but these oscillations are not acquired simultaneously. And you see actually, quite nice control on this 6-qubit device. The fidelities are just below or just above 3 nines across the 6 qubits. And also the visibilities are quite high. Visibilities are around 96%. And given that we initialize by measurement, our initialization and our measurement fidelities are roughly similar. So that means that you have about 99% initialization fidelity, 99% readout fidelity, and around 3 nines on the single qubit gate fidelity across the 6 qubits. We also prepared entangled states pairwise of the neighbors, reaching entanglement or state fidelities of these Bell states of let's say 88 to 95%. That's actually also an encouraging development. I just mentioned a couple of years ago on a 2-qubit device, we reached a 90% state fidelity on a 2-qubit, for a Bell state. And so now across a 6-qubit device, we actually do similar or better. That's of course the path that we need to be on. We need more qubits and at the same time improve the level of control. Not everything is just easy and perfect, as you might imagine. This is still experimental work. And here I want to mention one surprise that we came across. What we had observed across several generations of devices for many years, and other groups have found similar effects, is that when you drive your spins for a while using microwaves, especially during long sequences like randomized benchmarking sequences, the observation was that the qubit frequencies might actually start to shift. And here you see this kind of quantitatively, as you apply more pulses, sweeping either the duration or the amplitude of the pulses, where this number here corresponds to about 10 pi pulses, you see that the qubit frequency of qubit 2 in this case shifts by about 1 megahertz. We observed very similar patterns for the other 5 qubits on this device. After turning off the microwaves, that qubit frequency would, on a matter of milliseconds, return to the original value. It looks a lot like heating. The shifts are proportional to the energy that you put in, not the amplitude, the energy. There is this kind of slow return to the equilibrium value. And so we began to wonder, are our qubits really getting warmed up? If so, by how much? And so on. And so what we did was to change the temperature on the mixing chamber, change the temperature of the sample itself with an external heater. And we had no idea what to expect, but this is what we saw. This is up to 0.5 Kelvin. You see that the qubit frequencies initially increase by indeed about 1 megahertz, depending on the, around there. Around 200 or 300 millikelvin, plateau, and then slowly fall off. This was not expected. In our field, a lot of the progress has been has come from experimental predictions, from experimental proposals. Theory has played a big role in our field, but this was not anticipated. It's still not fully understood. We've put a lot of thought into the possible origins and could eliminate several possible origins and are still a bit uncertain. It's quite possible that it's a combination of two mechanisms, because any sensible physical mechanism that we can think of would give a monotonous temperature dependence, not a non-monotonous temperature dependence. So it's very striking. Actually, it's very striking and still to be further understood. But in the meantime, we're working from a rather surprising second pragmatic or second observation, which is, well, what if we bring our temperature of the mixing chamber to, let's say, 200 millikelvin? Will the sample still be just as sensitive to these microwave drives? And the answer is no, actually not. So when we operate at 200 millikelvin instead of at 50 millikelvin, the RF heating effects, right, from driving with the microwaves are pretty much gone. This is, well, up to some noise, a flat response. Even at 150 millikelvin, that's the case. At the same time, the T2 star, which might also be temperature dependent, is not really compromised yet, up to 200 millikelvin. And then most strikingly, because of these RF heating effects observed at base temperature, if you take a simple Rabi oscillation, it matters, you know, in which direction you accumulate the data points. Do you go from left to right or from right to left? It matters whether you wait for a short while between successive shots or give the system time to re-equilibrate. All these responses give you different Rabi oscillations. At 200 millikelvin, the same experiment, all the curves fall on top of each other. So that's quite interesting again. And so we're now continuing to measure on this sample, trying to run some quantum algorithms, dynamical quantum phase transitions. And we're doing this at 200 millikelvin because it's easier. The calibrations are just more steady, more reliable. All right. So moving on now to the quantum links. There are two ways in which we are trying to build quantum links. The first is to use superconducting resonators. This is, of course, directly inspired by all the beautiful work from the superconducting qubit community. And the other is to take an electron and shuttle it through a channel, displace it literally, trying to preserve the spin state. Let me start with the first, where there have been quite a few theoretical proposals for doing this. So you have to imagine a single electron spin is coupled to a resonator. A second single electron spin is coupled to a resonator. And the dream is that mediated by the resonator, the two spins will talk to each other, and that you could actually implement a 2-qubit gate between two spins on the same chip, but at a distance from each other, not at 100 nanometers, but at 100 micron or so from each other. And here's the device that we're using. You see here some of the surface gates that form a double dot at one end of the resonator. There is another end of the resonator with another double dot. The resonator in this case is just a piece of, well, a narrow wire made from niobium titanium nitride. We chose this material and the narrow cross-section to get a large kinetic inductance and also a large geometric inductance. In addition, the ground planes are far removed, so that lowers the capacitance, and together this gives you a large characteristic impedance of this resonator. Why do we want a large impedance? Because we need, let me take one step back. The microwave photon in such a resonator has, of course, an electric field component and a magnetic field component. It turns out that the magnetic field component of a single microwave photon couples super weakly to the electron spin. It's not going to be usable in this context. So instead, we like to use the electric field component. And so to maximize the electric field component, we maximize the characteristic impedance of the resonator. Like before, we need spin-orbit coupling or a micromagnet for the electric field to talk to the spin. That's why you see these two pieces of cobalt on top of the quantum dots. And so in this way, the microwave photons that interact with the charge of the electron indirectly also interact with the spin thanks to the field gradient. So that's the idea. First, result is that we can achieve the so-called strong coupling regime for the spin and the photon. You see here the resonator frequency probed in transmission, right? So we probe, well, we send energy into the resonator and measure energy coming out of the resonator. So we see here the response. And as we change the external magnetic field, at some point the spin frequency matches the resonator frequency. Instead of crossing, it actually shows an avoided crossing because the spin and the photon hybridize, and that's what you see here. And the fact that the separation between the branches is larger than the line width tells us we're in the strong coupling regime. This is for the left, or actually for the right electron, this is for the left electron. And when we allow both of them to interact with the resonator, we see an avoided crossing, which is enhanced by a factor √2. That's the collective enhancement. It's in general √n. Of course, n is 2 now. But so this is indicating that the spin, the photon, and the other spin are coherently interacting with each other. But now we go a step further, and similar results were obtained in the Princeton group a bit before. Now we go a step further and try to take out the resonator in the sense that we bring the two spins on resonance with each other, but detuned in energy from the resonator. So the resonator doesn't get populated, it only gets virtually occupied. And when you do that, you can probe with, by applying a second tone, you can probe the spin resonance frequency, the spin qubit frequency for one spin, for the other spin. And then when both are allowed to interact, again, instead of these two responses falling on top of each other and crossing, they show an avoided crossing. The lower branch is well visible, the upper branch is not, and it shouldn't be visible. It's supposed to be a dark state. By the way, the reason or the way that we control in a different way the spin splitting for the left and the right is by having different orientations of these micromagnets. And so if we then rotate the external magnetic field angle, the total field seen by the spins is evolving differently on the left and on the right. Okay, so this is all still spectroscopy. Can we actually use this interaction to see a gate in the time domain? And that's what we've done. This is still unpublished. What we will do is first allow both of these spins to relax to the ground state, then flip one of them using electric dipole spin resonance. Here, flip one of them, allow them to interact, and then read out one, read out the other, and plot the results. And so here you see how these two populations evolve in antiphase as a function of the time that we allow them to interact with each other. So in this case, what is it? Qubit 1 was flipped at the start, and qubit 2 started in the ground state, and you see them evolve in antiphase, and here it's the other way around. This is basically an I-swap evolution. It's described by the James-Cummings Hamiltonian, x plus y. To verify further that these oscillations come from the physics that we're expecting, we can change the parameters in several ways. For instance, what we can do is change the detuning between the spin and the cavity, right? So the two spins are on resonance with each other, and then you can change their detuning with respect to the cavity, and that in this case accelerates. Well, if you lower that detuning, then it accelerates the evolution as expected. The other thing you can do is change the detuning between the charged qubit and the photons, and that's in this case supposed to reduce the oscillation rate, and that's also what we're seeing. So all of this is making quantitative sense with the models that are there to describe this system. So that's kind of a novel result, two spins interacting coherently, 200 microns apart on the same chip. And look at the time scales, it's pretty fast, right? So this is tens of nanoseconds time scales. So then what about the other approach? This is work that we started quite some years ago, and actually Takafumi Fujita, who is now at Osaka University, was part of this. He performed measurements in a gallium arsenide quadruple dot device where he saw coherent or coherence, spin coherence survive when shuttling an electron from the left to the second, to the third and the fourth dot and back, and doing this repeatedly, and then looking at what this does to the spin phase. There have been many measurements on shuttling. Charges have been shuttled in devices with up to 9 quantum dots. In silicon, there has been work at Princeton and here at RIKEN, Tokyo RIKEN, looking at double dots, but then in silicon and looking quantitatively at how well spin is preserved. Here I want to show you results on a silicon device where we shuttle not just between 2 dots, but really shuttle across several dots. And the first experiment that I'm showing here is to look at the effect of shuttling on the spin polarization. So you see the linear array will move electrons back and forth through here. And I notice this picture can be confusing. Let's ignore the black line and just look at these colored dashed lines. For this line here, the electron spends 50 milliseconds in total in the array. And the horizontal axis tells you how many times we go back and forth through the array. And so what you notice is that regardless of how many times we shuttle back and forth, that spin projection stays unchanged. The same if the electron spends 100 milliseconds or 150 milliseconds in the device. Of course, the difference between these lines is that because of relaxation, when the electron stays in place, there is a lower spin-up fraction here, but it's not dependent or not changing with the number of times that we hop back and forth. This is just looking at the spin projection. What about the spin phase? This is very preliminary data, and so these numbers are going to improve, I'm quite sure. Actually, a new Japanese postdoc, Yuta Matsumoto, who started just half a year ago, or no, a few months ago, has joined this experiment. And here we're looking at the spin phase basically studying how the spin phase is affected by hopping. In this case, there is an effect from hopping, and that's expected. We know that it depends on exactly how you implement the shuttling. You need to get the tunnel couplings right and do things gently and so forth. So there is room for improvement, and we will use that room to push these numbers up further. But I wanted to share this preliminary data. So I have some time left for covering another topic, but I want to first summarize here and the part on quantum computing. It feels to me that in our group, but really also as a community, we are implementing these elements of the vision one after another and are able more and more to bring them together into a single experiment. And that's just good to see. And of course, that's what we need to do. So specifically, gate fidelities, single and 2-qubit gate fidelities are now reproducibly high. We can control up to 6 qubits, show universal control of up to 6 qubits. We can couple spins at a distance as one path and shuttle electrons around as 2 paths to creating links between registers on the same chip. What I didn't have time to cover is that we have been collaborating with Intel for quite some years, and together showed that devices made in their advanced manufacturing facilities with all the same technology as they use to fabricate integrated circuits can match the quality of devices made in academic groups, but with a yield which is just a whole other level. I also didn't have time to tell you about how qubits function at higher temperatures. There will, if you have onboard electronics, the temperature of the chip will go up. So didn't discuss that, and also not the work on integrating some of this cryo-CMOS electronics. But even though I didn't show everything, there is progress along all of these fronts, and so that's encouraging. I did want to use the remaining time to tell you about a different line of research that uses the very same quantum dot platform, not for building qubits, but as emulators, as a quantum simulation platform of Fermi-Hubbard physics. You know, the Fermi-Hubbard model, of course, a very famous model in condensed matter physics. In its simplest form, it has just these two middle terms here, where particles can move around on a lattice, hop from one side to another side, to a neighboring side, and where there is an energy penalty, or gain actually, for two particles to come together on the same side. These terms are naturally given in our quantum dot platform. The hopping is the tunneling between sides, between quantum dots, and then the on-site interaction is given by the Coulomb interaction. In many of the real systems that are described by Fermi-Hubbard type Hamiltonians, the physics is richer than that captured by these two terms. Often there is also a long-range interaction. And of course, the long-range interaction also exists in our platform. Particles, electrons still feel each other if they're on adjacent sites or even on the next neighbor site and so on. And then finally, the system gets richer if you can modulate the potential of each of the sites. And so in our platform, the first and the second term are tunable in situ when the device is called. The other terms can be changed by the design and don't change that much when you're operating a given device. We have performed a number of experiments looking at different aspects of this Fermi-Hubbard Hamiltonian. The first one was dominated by interaction energies, sort of, you could say, Mott-Insulator type physics. The second, this was actually a very nice experiment proposed by Eugene Demler many years ago when I visited MIT and Harvard. Here we saw a form of magnetism predicted more than 50 years ago by Nagaoka, and that had not been seen directly in any physical system. And we could, in its smallest incarnation, make it visible in a 2x2 quantum dot plaquette. And more recently, we've been studying the Heisenberg spin chain, so 4 electrons in a 4 linear dot array. And there has been independent work, by several groups. You saw the work from Michelle Simmons, which is dominated. Oops, I indicated here, or I classified it, by which term is dominating. U dominates, hopping dominates, or J. J doesn't appear here directly, but of course, as we know from our spin qubit experiments, J is the spin exchange interaction that arises from virtual hopping of electrons between sites and is, scales as t squared over u. So what I do want to spend a bit more time on is a experiment that's actually now on archive as of 1 or 2 weeks ago. This is on a device built in germanium, again, heterostructure grown by Giordano Scapucci, and the device was fabricated in the Veldhorst group. And it's a bilinear array, so a ladder device of 8 quantum dots with 4 sensors around it. And again, proposed by Eugene Demler, we performed an experiment, and here we take steps at studying exciton physics in this platform. So what we do is basically to fill the top channel. Okay, so we're going to tune the device in a regime where the tunnel couplings along the top leg of the ladder are activated. Also for the bottom leg, they're activated, and the tunnel couplings connecting the legs are made very small. With the gate voltages, we can do that. So we made these very small, and then we've occupied the top channel with one hole everywhere. These are holes in germanium, and the bottom channel is empty. Then with the gate voltages, we will push out a hole from one of the sides. And we can, with the gate voltages, we can move that hole around. Depending on how you tune the bottom channel, the presence or absence of these holes here will have an impact on the potential of the sides across in the bottom channel. But in this condition over here, it has no consequences. On the other hand, in this condition over here, the levels of the bottom channel are very close to being filled. And so when a single hole is pushed out here, a hole will actually appear at the other side. So a single hole that's removed from a filled band, that's actually an electron. So we have an electron and a hole together forming an exciton. And if we drag the charge carrier at the top, if we drag it around using the gate voltages, then the opposite charge in the opposite channel will follow. So it's really a weakly bound electron hole pair. And we see this in the experiment. We measure here the signal of the bottom left sensor, right over here, and the bottom right sensor. In the bottom left sensor, what you see is at the top, the signal when a single charge is pushed out and then is moved farther and farther away. At the bottom here, an opposite charge can enter, and then it actually overcompensates the signal from the top channel, right? Because this is closer to the bottom sensor, so that's why you get a yellow signal. And just like the dark blue here fades out, here the bright yellow fades out as this net positive charge moves away. So this is kind of all consistent with excitons forming and being dragged around through this channel. So with this, my time is up. Here's the summary. Maybe I'll just leave it up there for you to read, and thank the group that contributed to these results. As many of the experimentalists have experienced, sometimes it feels like you're stuck in the mud, but eventually you come out, and I'm certainly very thankful for all their contributions, as for the contributions of many collaborators on the various projects. So thank you for your attention.